The logarithm has been a tool for mathematicians, physicists, and engineers around the world, simplifying calculations to a much more user-friendly form. In the history of the logarithm, John Napier was the first mathematician to devise the idea of the logarithm, who gave technical expression to his concept. He covered a term from the two ancient Greek terms logo, meaning proportion, and arithmo, meaning number, compounding them to produce the word logarithm.
As a simple definition, logarithmic functions are the inverses of exponential functions. The logarithmic function y is equal log ax is defined to be equivalent to the exponential equation y is equal to the x power of a. Y is equal log ax only under the following conditions. Y is equal to the x power of a, and a larger than 0 and a not equal 1. It is called the logarithmic functions with base a.
These are several properties of logarithm, which are widely used in some complex calculation. Later on, we are going to apply the third formula to solve a question. Normally, we call the log based on 10 as log x. Especially, we call the log based on e as ln x, which is also called Naperian logarithm. Here, e is an infinite non-repeating decimals, which is originally used to calculate the infinite compound interest. Let's put these properties into practice. Here's a financial question. As for the time that an investor would need to earn $200 of compound interest, we use the formula for future value here and substitute the numbers, we get this formula. Simplify it, we get this. It is hard to calculate the value of t in such an equation, so we need a logarithm now. We add a log based on 10 on both sides. The properties we introduced above allows us to put the two t's in front of the log. Then simplify it. Finally, we get the t. We couldn't have done it without logarithm.
This is the graph of the logarithm. As the base changes, the curves go in opposite directions, but all curves have a common intersection, which is 1, 0.
And now, I'm going to start with another application of the logarithmic return using stock market modeling. First, we're going to compare the differences between arithmetic rates of return and logarithmic rates of return. Imagine there's a stock A. Its price is 10 in day 0. In day 1, the price for stock A increased by 10%. However, because of the market crisis, the price in day 2 is 10% lower than the price in day 1. In other words, the rate of return goes up 10% and down 10%. If we use arithmetic method, the total return of the first 2 days should be 0%, but the actual return is not. Well, on the other hand, if we take natural logarithm of the daily return and add them up, as it can be seen in the table, it gives us the return close to the actual return. And as the formula appears, because the daily logarithm return is symmetric, and we can simply add them up to get the total return. In this case, for arithmetic return and logarithmic return, as return get further away from 0, these two formulations will produce increasingly different answers. Log returns are far superior to the arithmetic return, since it calculates the continuous compounding return, and sum of return is normally distributed, but the other is not.
Okay. 凑团。